Okay, welcome to the complete Mechanics of Materials Exam 1 study guide. So what I'm going to do is I'm going to go through all three chapters, get all the formulas from each of them, then I'm going to tackle some of the questions from each of the chapters and try to apply the knowledge. So right here, let's make our formula sheet. This is going to be the formula sheet. Let me make sure that that's good. Make that a little smaller maybe though. That's probably fine. Okay, so this is the chapter 1 of the Mechanics of Materials. And pretty much this chapter is just about, I guess, stress. Normal stress, bearing stress. I feel like that, and that's axial stress and all these other things. So stress analysis. So let's see. Mechanics of Materials. This is kind of just going over what this is. And yes, of course, it's going to take a lot of statics. So we're going to need to remember our basic formulas for statics. I probably would put the law of sine and cosine on this, actually. Now that I think about it, that might be useful in some of the statics applications. Of course, drawing free body diagrams. This goes back to statics and physics. But we're jumping right into an example. It says, consider the following structure. Oh, wait. Sorry. I forgot. We're going to be breaking this up into 50-minute study, 10-minute break. That way we get optimal, I don't know, brain function. So, all right, study begins now. Hold it. Control. I can probably just, Control F. There. Now you guys can see that. So, yeah, consider the following structure. Joints at A, B, and C are frictionless. Load at P is 4,000 pounds. Find the forces at A and B acting on the beam AB. So I guess I don't, we could go through this example actually. So why don't we? Maybe to save time, because that would be a while, and we're gonna go through problems anyway. We can just look at what they do here. So we have AX and AY, and then over here we've got tension Y and tension X, but we can also just call this tension theta, right? And what are we trying to find? Forces at A and B. So immediately, if we take the forces in X, there's only two. Forces in Y, there's only two. Or actually, we could think about this, instead of tension being made into theta, it's tension in theta split up into X and Y components. That's the more accurate description. And of course, also the forces in the Y, which is also a P. Yes, there is force P right here. You can almost not see it right there in like magenta purple. So P going down. So Ty plus Ay minus P is equal to 0, since this is in static equilibrium. All the forces have to equal 0, which we see here. Now we take the moment about point A. This should eliminate A and B and give us tension. So we're solving for tension in Y. And finding tension in Y, let's see. 4,000 plus AY minus 4,000, AY equals 0. So because AY equals 0, TY is equal to P, right? Yeah, that would make sense. TX equals TY, so P equals TY equals TX equals AX. So yeah, they all equal 4,000, if that makes sense. But that's just going over a problem. I don't think that's just that right here. This is just statics review. This is just statics review. Analysis of internal forces. So consider at A, we have 1 kilonewton force, which means there's going to be a reaction at A if we just analyze this here. 1 kilonewton force here, 2 kilonewton force here. So there has to be something counteracting that equally, which would be a 3 kilonewton force reaction, or kilonewton reaction. And now let's do this about B. There's 5, 1, and 3, 5, 6, 7, 8. There's going to be an 8 kilonewton reaction force at B. So there's that. Now, stress, definition and types. Axial loaded members. So if we have like a rod, along its length on the very ends, getting pushed in would compress the rod, and on its ends, getting pulled away would cause tension. And here are axial loaded members right there. There's one, and there's one. It says here. And finally, we're getting into what this chapter is really about. Here is the equations. Equations. My favorite mechanics of materials. Okay, so our first equation, we write down normal stress is this thing equals P over A. This is internal force over cross-sectional area. Here are its units: kilopascal, megapascal, gigapascal, psi, ksi, or yeah, 1 ksi is equal to 1000 psi. Stress analysis helps you design elements. We might have to use this to be asked what diameter something should be if we have this much stress and other things. So normal stress on axial load, small area delta A, forces delta F. Then the change in stress is the change in force over the change in area. Combine all such stress contributions. So stress average is P over A. P is stress average times A. So here in example 3, where was example 2? Example 1? I guess this is example 2. So example 3, 2 solid cylindrical rods AB and BC are welded together at B and loaded as shown, knowing that the average normal stress must not exceed 150 megapascal in either rod. Determine the smallest allowable values of the diameter. So here we are. We're given stresses and we're asked to find the diameters. So we have, let's see, the stress. So stress is equal to 150. And what are the forces? We have forces here and forces here. So we have the forces and we have the stress. So we're trying to solve for area. Area of a cylinder cross-sectional is a circle. So the area of a circle is going to be pi r squared, or pi diameter squared over 4, all of it over 4. Those are going to be our formulas. I think they write it as pi over 4 times diameter squared, which is essentially the same thing mathematically. It just looks like it might be easier to break that apart and write down our special numbers, or our values, I mean. So we have rod AB, here's BC. We're breaking rod AB up. So rod AB is broken up, interestingly enough, has only one force here acting on it. We're not taking into account the forces that are along where we're splitting this up. So rod AB has a reactionary force P of 60. Which means for rod AB, 150 equals this force 60, over pi for diameter squared. We're trying to solve for diameter squared, so we set up the equation this way. And taking the square root of this, we get this to be the diameter in meters, and we're solving it in millimeters here. And now the same for BC, taking it all the way at the reaction at C, we have to now account for all of the forces. So we have 120 to 125, dual 125 forces and a 60. So it's going to be 60, all of this minus 60, or minus 60 plus all of this, plus P equals 0. So P would equal 60 minus 125 minus 125. Yeah, that makes sense. So P is negative 190. We set the stress up here. Looks like we take the negative out since we're really, what is this? Stress. I guess stress can't be a negative value, so we always kind of take the absolute value of the forces we're given, or maybe it's because we can't have a negative force. Force is just direction, and positive and negative. So that could also be it. So we have 190, 150, and then we're trying to solve for this here. So we set up the same way, square root, and this is how we get our second diameter, and that is how you solve that example. Here's another example here. It looks like we're given P and A, and we're just solving for it. We're given force. Force is always, no, area is always 3. The forces are different along each. Must be given them here, or solving for them here. I can't really see this problem very well, but here's the problem, and here's how it's solved. Again, here, this is going to be statics, and it looks like we did the method of sections. Okay, so this is going to be like a method of sections. Let's see. So they want the entire truss. This is going over the method of sections. So yeah, entire truss, AX, AY, and then this is a roller, so it's only going to be up. This is like a pin joint, so it's going to have AX and AY. This one's just going to have up and down because it's a roller. So AX, AY, there's no opposing force in the X direction, so AX equals 0. And then we have this point H and AY. It looks like we take the moments about H. So from H, R cross F of 90. So, or is that 80? Yeah. 9 times 80, 18 times 80, and then 27 times 80, and then 36 AY. So solve for AY. AY is 120 kips. Now that we know AY, we've got these forces here, and we know their angles, height of 12, length of 9, it looks like. EE. Why is it 15? 12/15ths. Oh, because we know this and we know this, so a squared plus b squared equals c squared, right? So then this has got to be, no, I would say it's going to have to be tangent opposite over adjacent. Opposite is 12, adjacent is not 15. But they say it's 15. Oh, right here. They did do that. A squared plus b squared equals c squared. So they're not doing that. They're doing sine and cosine. That's the functions we're trying to find. We're not trying to find the angle. We're just directly plugging in sine, cosine. Sine's up and down, cosine's left and right. So forces in the y, we want the sine function. So sine, so katoa, opposite over hypotenuse. Opposite hypotenuse. Opposite over hypotenuse. And yep, that is indeed what we have here. So using this now, they solve for FBE. We know it's going to be AY is one of the forces in Y. 80 is one of the forces in Y. And if you look, FCE and FBD are only in the X direction. FBE is the only one that has a horizontal component. So we can solve for FBE right now. And And we have the force of, oh, and that's the only member we have to find, so that's actually really good. So now that we know FBE, we get the force of FBE over the cross-sectional area. We're given the area, so we take the 50 kips, we put it over the area, and that is the stress in member BE. Average shearing stress. Here's another equation. Finally, we get to another equation. Okay. Now V is the internal shear force over, I believe it's still going to be cross-sectional area. So let's see what it says here. Average shear stress. So consider the effect applying force to F. If F is large enough, it can cause the material of the bar to deform and fail along the planes identified by AB. So it's the planes that are not supported then. Just this section here. The average shear stress is given by the formula tau average is equal to V over A. Transverse load causes shear stress. So I guess loads that are not on the same plane vertically, if they're being applied vertically, if they're shifted one to the right and one to the left and both applied in opposite directions, that would be the transverse load. That's what I'm seeing here. It's almost like a couple if we think back to statics. And here we're talking about pins, bolts, rivets. I'm not sure what elements is, but they're also listing elements. And here we have single shear, and we're going to get to double shear. And this is where the tau average really comes in when we're going to need it, really. Single shear is load applied in one plane. When single cross-section of an element in a joint takes all the shear force, it's called single shear. So this is like one pin supporting the entirety of the shearing force. So that would be the single shear. Double shear is when two cross sections of an element are subject to the shear load. It is called double shear. Double shear is safer and has higher factor of safety. So do you see how this is a single pin getting pulled apart by two forces? If you look here, it's I guess it's still a single pin, but there's two objects. This object is covering here, and then this object is also being covered. So we have, looks like actually a larger area that is being pulled apart across for the force, which I guess is why it would be much safer. Because the force, I guess, is being spread out more. So there's less stress on any one particular point. And here's examples of single and double shear. Double shear right here. Single shear right here. Okay. See, force, so two forces on this side, one on this side, and this is just single forces, like a single couple. I guess that could be one way of identifying these, since as you can see here, it's kind of the same story. Single force in the center with two forces on the outside. Single force center, two on the outside. So kind of an identifiable pattern if we want to use pattern recognition. Example 6. For the assembly and loading problem 1.7, determine average shearing stress in pin B, average bearing stress B, remember BD, average bearing, did we already go over bearing stress? Shearing stress, normal stress. I don't think we've gone over bearing stress. So is this how we learn about bearing stress? We should be given the equation. Yeah. Where is it? I swear, I didn't skip it. Shearing stress, bearing stress. It's going to be like the thickness times the diameter. You'll see. Bearing stress. We have a thickness and a diameter. We should write down bearing stress. What's the formula? Oh, it's given after ask the question about it. Bearing stress, pressure, force, area, but here. They did a lowercase b. Force over thickness and diameter, I believe. Thickness, yeah, thickness of the plate times the diameter of the pin slash bolt. Yep, thickness of plate, diameter of the hole in the plate, or of the bolt. So coming back up here, very difficult to see. We're given the thickness. Thickness is 8 millimeters. It's probably given somewhere. Oh, it's up here. Yep. Area, 8 times 36. And here's the D, so we find the forces. Are they given? This looks like a 4. I can't really see. I'm so sorry. But here you can see the work through here. FBD over 2 dt. Would this be because this is shearing and this is bearing? This part A. Okay. Interesting. Normal stress for axial loading was calculated. Stress average P over A. Stress on oblique / inclined plane. So here it is, a plane that's at an angle like how them katana swords cut those canvas, little circles of canvas, how they're always at that angle. It's all I can think of when I see things like this. So I guess think of that too. So here's an example here, and the formula for stress on an inclined plane. So I think there's going to be 2. This is going to be E over A0 cosine squared theta. And then also going to write this is normal, and here's shearing. Okay. Here's this example. We're given the shearing stress, the normal stress. We're given the outer diameter. And it looks like the thickness, or is that from this problem? No, that's here, right here. And a diameter inner of, geez, how did we find that? We have the angle. We're trying to determine what the maximum value of P is. So 10 millimeter thickness right there. 20. Where did we get the radius inner from? Oh, I guess it's going to be 400 minus 10. So that would be, overall, it would be 380. Yeah, because it would be minus 10 this way. And then we'd go over the empty cavern, and then minus 10 this way, and then we hit the outer radius. So yes, diameter inner would be 380. And A0 here is pi r0 squared minus r initial squared. That could be useful for finding the area 0 of a hollow pipe. And then we just plug the angle in, plug in the tau and the normal stress, and manipulate the equation to get P, and then we solve for P. And then of these, when it says asked what's the largest axial force, they do not mean the largest value you find. Because here we have P is 833 kilonewtons, and here we have P is 1372 kilonewtons. What they want to know, right, is the largest. I'm trying to think of how to word this. Remember that when they ask the largest force, you give your smallest answer. I guess this is for safety. Because if you had this force here, right, and say one of the stresses can only be 833, but you applied this force, then you would actually be exceeding what this stress here can handle. So you can't exceed that. Right? If one of your forces says it can be this, but the other one says that it can be something lesser, you have to do the lesser one. Because picking this would not be safe because this one cannot support as much as this one can. So you always pick the lowest one. And this is the maximum that the actual pipe can handle without one of the stresses being completely overloaded. So yes, that is why when they ask what the largest value is, you give the smallest of your answers. And now it's moving on to the analysis versus design. I'm just reading this out. Analysis, the structural member or part is completely designed and checked to ensure it's safe and intended for use. Possible modes of failure: fracture, excessive deformation, buckling. Actual stress should be less than the allowable stress by design. Now design. Engineers select appropriate components for intended use, suitable material, suitable shape and dimensions, and allowable loads. What's an allowable load? Maximum load that a structural or structure member or machine will be allowed to carry under normal conditions of utilization or intended use. ASD, allowable stress design. LRFD, load and resistance factor design. And a factor of safety, I'm also going to put this on the formula sheet. Factor of safety is equal to stress ultimate over stress allowable. Okay, that's the factor of safety. And a lot of times we're given the factor of safety, and we need to split the factor of safety up because we want to be given the ultimate stress or the allowable stress, and knowing what the factor of safety is, we can actually figure out what ratio we need to have, say for the one we're missing, the ultimate or the allowable. So it's important to know what the factor of safety is because we might be given it as a number and required to solve some kind of a stress problem given other I don't know, numbers, other variables. So factor of safety, structural members or machines must be designed such that the working stresses are less than the ultimate strength of the material. Factor of safety considerations: uncertainty in the material properties, uncertainty of loadings, uncertainty of analyses, number of loading cycles, types of failure, maintenance required, and deterioration effects, importance of member to structure's integrity, risk to life and property, influence on machine function. Okay, and here's example 8. Solve problem 1.15, assuming that the structure has been redesigned to use 5/16 inch diameter pins at A and C as well as at B, and no other changes have been made. And here we have this long detail word problem here and a little diagram. Link AC made of steel, 65 KSI. Ultimate stress, so here's the ultimate stress. And here's the cross section. Connected to support A and B. Here's the diameter pins, but we're saying that they've been changed to 5/16, right? All the pins are made of steel with a 15 KSI, so there's the ultimate stress. And we're also given that they're in single shear. Oh, I forgot to write single shear versus double. Let's go back up. Double shear. Okay, so that one's for double shear. There. Moving back down. So here, let's see, we're given force P. And we're given the factor of safety. Okay. Link AC is not reinforced around the pinholes. Okay. So, looks like we take the moments about B. This should get rid of AX as well. So we'd only have, or AY, so we'd only have AX. And P, so I think overall we're trying to solve, let's see. minus 10p plus 6. And then we have probably the cosine. So that would be, so adjacent over hypotenuse, so that would be 8 or 10. And from here, looks like we just get FAC in terms of P. And then do we know what P is? So we might not. But we have FAC in terms of P. Some of the forces in the x direction. BX, where's AX? They're only looking at BCD. Okay, that makes sense. So BCD we wouldn't worry about AX anyway. So here we have BX, and then the cosine of FAC, which is here, and we have that in terms of P. So we have BX, we can get BX in terms of P, which we do right here, it's 5/4 P. Some of the forces in the Y, we get BY in terms of P. So we can get B in terms of BX squared plus BY squared square root. We replace P, and now we have B in terms of P. So now with our pin B, we have our ultimate over our, what does it say, over factor of safety? Shouldn't this be ultimate over allowable? Because that's what factor of safety is? Tau ultimate over factor of safety. That would just be the allowable. Tau ultimate over the tau allowable. Okay, that kind of makes sense. If we have factor of safety divided by factor of safety divided by, or if we have ultimate divided by factor of safety, it's ultimate divided by ultimate divided by allowable, which would be the same as, I think that would just cancel the ultimates. It would be stress over allowable, or that might work. Tau ultimate over the factor of safety. Interesting. Factor of safety is 3.25. Let me just use this really quick. Ultimate over allowable. Keep this, change this, flip this. This would be the allowable. Well, they use this to solve for P. And now that they have P, they can also look at the shearing at pin C. Factor of safety is ultimate over allowable. How ultimate is TU over factor of safety. So yeah, that is exactly what we found. And yep, they solve for P here also. So this is at B, this is at C. Normal stress in AC, ultimate over factor of safety, FAC over the area. FAC is going to be 100 over 48, P 3 over 36 for the area. And then here we have 65 for the ultimate and the factor of safety. So plugging it all in, here we have the normal stress in AC and the Smallest value we get is 0.283. So the maximum allowable load is 0.283. Remember, when they ask for maximum, you give them minimum. That all tracks. That all makes sense a little bit. And here we are. Here's the end. Here's summary. We might be able to go through this problem, but we can just find one on the homework that does the same thing. So here we have normal stress, which we have, shearing stress, which we have, and double shear. Bearing stress, right here. Stress on an inclined plane. We have normal, and we have shearing. And we know the factor of safety. So that is Chapter 1 for the mechanics of materials. And we have about 10 minutes left before our break. So that means we can start solving problems. Okay. Here's our first problem. So we have two solid cylindrical rods AB and BC welded together at B. We're given P. P is equal to 14 kips. That doesn't quite look right. Kips. And let's see, we have that's close enough. This is going to be a B with force here. And then we're going to also have kips, 12 kips. It's going to be RA, and this one's going to also be RA. It's going to be 12 kips, and then this is also going to be P, but we know that P is 14 kips, so we can write 14 here, and this is in terms of kips, this whole thing. So for just AB, see, for AB, we probably have to look at the whole thing. The next one's going to ask in CD, AB. Yeah, we probably still want the whole thing, right? I'm going to say we probably want the whole thing. So this would give us the reaction at A. So here, for this one, RA equals 12, right? So we have P. We can actually just call this P. I take it back. P equals 12. So if we know normal stress is going to be equal to P, we're A, then for AB only, not looking at the entire structure of A, B, and C, for just looking at the forces on A to B, then we have P is 12. And area is going to be, well, we have 1.25 inches, pi times r. Well, what's 1/2 of 1.25? We could just use the diameter equation. So it would be pi over 4 times the diameter, 1.25 squared. And what's this whole thing equal to? Yes, calculator. F(y) equals pi 4 times 1.25 squared. I'm not getting the right answer. So maybe let's take a look at the whole thing. RA here, or P, is going to equal 12 plus 14. So if we instead do 12 plus 14 on the top, and in fact, we are getting 21.186 KSI. So it looks like when they're asking about point B here, they want the whole deformation, the entire stress. I guess it's not deformation, but it's stress in the object. So let's see the part B of this. Okay, P equals 14. Okay, same thing, but now they're looking for BC. So what was the first one? At section AB? At rod AB. Now they want to know rod BC, so they want to know this rod here. First one was this, now they want this one. So here, well, if we just look at this rod here, we have 14. And we have force P here. So what we could say then is, do we have to do the whole entire object? The stress on BC. Oh, let's try just 14 and let's see what we get. And this is going to be pi over 4 times the diameter of 0.75 squared. Now let's see what we get. And indeed, I'm getting that stress is equal to 31.689 KSI. Interesting. Very interesting. So when we're given this one, we take the whole object. When we're given this one, we just need to find the stress in just this one object. We don't need to worry about all the rest here. I guess that this is because it's a fixed support. That means that there's a reaction here, and it has to counteract everything. But this doesn't have a reaction on this, so it only has to counteract its own force. So that makes sense. If there was another support here, maybe that would be a different story. And I think that is why these problems are like this. So, all right, I'm going to end it a little bit early because my throat was getting a little bit hoarse and I'm going to get some milk. So, BRB then, break a little early. Okay, back to the study. So, mechanics of materials. Schwaza. Chapter 2. So, chapter 2, this is all about strain. Poisson's ratio, shear strain, composite materials, Saint Venant's principle. Everything in this chapter is about deformation, right? That's the big thing. Deformation. So, strain. Strain's a measurement of deformation of a body which undergoes elongation, contraction, or twisted through a certain angle. Types of strain, there's normal strain, which is epsilon, and shear strain, which is gamma. Study strain in non-rigid objects. So these are the two things we have to do. Study strain in non-rigid objects due to stress, and define and understand strain. So, normal strain is the deformation of a body which involves elongation or contraction. Tensile load, tensile stress, elongation, compressive load, compressive stress, contraction. These are the pipelines, people. And the change in length is this guy. It's like a sigma, but I'm just going to call it just like the deformation. Is length final minus length initial. Engineering strain, epsilon, is change in length over original length, which is in inches and inches, or inches per inch, or millimeters per millimeter. So that's a really, really good thing. We're going to, let's see. What's this one? It's a line tool? No, it's eraser. Oh, geez. I don't know what that is. Let's just draw. Whoa. I have a real eraser, actually. I put a real eraser down. It's funny. Right there. Okay. This is chapter 1 stuff. This is now chapter 2 stuff. So we have engineering strain. Geez, that S just looks like a strain S, doesn't it? Equals strain over length, or change in length over original length. Normal strain, here we see that this is the original length, here is the new length, and boom, that right there, that's the strain. There it is. There it is. Twice the length in the same materials, twice the strain. It looks like twice the area and twice the load is the same strain. Interesting. Here we have the world's coolest pen spinning pen right here. And we use this to look at strain. And this image goes to Mexico every time you put the mouse over it. So, stress strain diagram. Ductile materials, okay? Hooke's law. E epsilon. F equals negative kx. We're going to have so many things to learn here. Shape, stress over strain is E, which is Young's modulus, or the modulus of elasticity. And Hooke's law is that stress is equal to E, what's this thing called again? E strain. Young's modulus times strain, I guess. Modulus of elasticity is the slope of stress times the strain curve. And F is negative kx. Elastic limit, E is, look at that, what's that right there? It's the same thing as the shape here, modulus of elasticity. Yield point material will have large strain ratio for small stress. So here we have stress ultimate right there. Yeah. And the yield strength, I guess, or yield, was that be yield stress right there? Yield strength right there over, this is yield stress, stress ultimate, ultimate strength. Interesting. Yield strength. Oh no, that is not stress, that is strength. Weird. Yield strength, stress Y, stress at yield point. After yield point, elastic deformation begins. Right there. This would all be deformation then. Strain hardening, necking, fracture. No, it would be here then. Necking, that's the deformation. Interesting. Ultimate strength, max stress, stress ultimate. Necking, the decrease of the cross-sectional area. So think of like a rubber band. When you pull on a rubber band, as you pull on the rubber band, it gets thinner as it stretches. If you look right in the center of the rubber band as you pull your hands apart, it gets thinner in the center. That is what we're talking about. It's the decrease of cross-sectional area, or decrease in cross-section. I don't know if it'd be cross-sectional area, but the cross-section, the thickness, the width decreases. Fracture, and this will tell you ductile or brittle. Percent elongation, length final minus length initial over length initial times 100. Reduction in area, area initial minus area final over area initial times 100. And the measure of ductility, 5% elongation, ductile, and 50% reduction in area. This is how you define something as ductile. Stress strain diagrams for brittle is a lot different. It just goes up and then done. Here we have a lot going on. It hits a yield strength, dips for a second, goes back up, and then here we have strain hardening, necking, and then fracture. Brittle materials seem to follow almost a linear curve, and then right there at the ultimate strain, ultimate stress, we have the rupture, and here's Hooke's law, modulus of elasticity. E is stress over strain, PSI, KSI over no units. Strength is affected by alloying, heat treating, manufacturing process, modulus of rest, but stiffness, modulus of elasticity, is not. So here we have the first major formula that we're going to use a ton, and that is deformation equals plea. Actually, hold on. I forgot to say equals E. There. Now we have deformation, or what would I even call that? Yeah, I guess deformation's a perfectly fine thing. Strain, deformation, strain, it's the same thing. Is plea. And here we have a 4-foot long wire, 1/4 inch diameter, is subjected to a 750-pound tensile load. Knowing that E is 29 times 10 to the 6, determine the elongation and the corresponding normal stress. So P, that's our load, 750. L, length, 4.8 feet. We convert this, what's 4.8 times 12? 4.8 times 12. Looks like we've converted this into inches. So 57.6 inches is the same as 4.8 feet. And that's over E, which we're given is 29 times 10 to the 6 psi. And then we're also given the diameter. So the area is going to be pi over 4 diameter squared. So right there with everything we're given, we can immediately get the elongation, which is the same as the deformation, which is the same as the strain. And now they want to know what's the corresponding normal stress. Well, we know that stress from all the way up here is force over the area. We have found the area here, so this area is the same. Boom, boom, plug that in. And we're given also the force, 750. So boom, with everything that we're given, we can just plug and chug with the right equations. For example 2, two gauge marks are placed 250 meters apart on a 12 millimeter diameter aluminum rod with E being 750 gigapascals and the ultimate strength being 140 megapascals, knowing the distance between the gauge marks is 250.28 millimeters. After a load is applied, determine the stress in the rod and the factor of safety. So we should write that stress equals this, which equals epsilon E, which equals strain over length times E. Okay, now with this, we have E. We're given the deformation, which is length final, length initial, which we could also write that deformation here. Oh, did I already pass it? Similarly, deformation equals length final minus length initial. So we have deformation right there. Deformation times length. So here's the original length times E, which is here, which is what we're given here. That's the stress. So we have the stress, now the factor of safety. That's stress ultimate versus stress allowable. We know the ultimate stress, 140. What we just found here, that's the stress that we found, so we plugged it in for the allowable. And here we have the factor of safety of 1.712. Example 3, look at this. This one is a classic. This one's kind of what we're going to be looking at. This almost looks like it could take a stress-strain diagram. Here we go. This is why I hate chapter 2. That's a stress-strain diagram. Deflection diagram. I mean, sorry. So here we're probably going to want to know side, angle, side, the law of sines, law of cosines. We're going to have to remember some of our statics and trigonometry. Chapter 2 is going to be very big on trigonometry because we're going to be using deflection diagrams, and pretty much a lot of problems, if they don't use deflection diagrams, are still going to be some kind of a triangle. As we see here, this is as triangular as you can make a problem. So we take the, let's see, 4 millimeter diameter cable, BC, is made of steel. E is equal to 200 gigapascal, knowing the maximum stress in the cable must not exceed 190 megapascal, and the elongation in the cable must not exceed 6 millimeters. Find the maximum load P that can be applied as shown. So let's see. We take the moments about A, which gets rid of AX and AY. It looks like it would also get rid of BY, so we'd be finding BX. Or actually, we don't have reactions at B. That would be FBC. That would be the cosine of FBC. So what we have there is we're going to be solving for FBC, looks like in terms of P. But we actually have that the cable must not exceed 190. So we can probably solve, we can say that P would probably equal 190, right? No, stress equals 190. P equals 0. Yes, we're solving for P in terms of FBC. And then we're going to put that in for the, what is it, for the, we can solve for FBC knowing we have the stress in the cable is 190. We have the area of the cable, and we know that the force applied on it is FBC. So we can solve for FBC, and then now that we know FBC, we plug that back in for P, and now we know our force P. So we can plug P in, let's see. No, because, oh, that's P. Yeah, that's, okay, that's maximum load. We're going to also find strain. So it cannot exceed 6 millimeters, so PLE. 6 equals PLEA. Looks like we know all of them except for the FBC. That's what we'd have to find. We know length BC, EBC, and ABC. So right here we have 2091.2, and here we have newtons. So that's 2.09 kilonewtons, 1.989 kilonewtons here. So it looks like the maximum load for FBC is here. And this is the load that we have on FBC. I don't know if we would need to have found that first for any of this. I think we could actually just start in with the elongation, no, E, A. We could find that right away. Okay. And this problem, example 4, killer, absolutely monstrous, horrific, horrifying problem. Link BD made of brass, we have the E of the brass, cross-sectional area. Link CD made of aluminum, we have the E of aluminum, cross-sectional area. Knowing they should support rigid member ABC, determine the maximum force P. It can be applied vertically at point A if the deflection of A is not to exceed 0.35 millimeters. So with this here, it looks like we can just take the moments. Once we take the moments, we can get FCE in terms of P, and then we can get FBD in terms of P. I think that's all, yeah, that's all just like reduced lengths. So that's how we solve for those. And now the elongation in length BD. Here we have the elongation equation right here. Plug everything in. We have that in terms of P. Same thing for this. Get this in terms of P. Now we have all of these numbers here. Deformation in B, in C, and in A, it cannot exceed 0.35. Deflection diagram time. We do this weird monstrosity. Pretty much this is how you summon demons, as you write this. This is all from a demonology book. This here symbol. Everything needs to be drawn here just as shown, and by then you should get this demon that spawns from writing this. The deflection diagram demon, right? And using this, we can actually find the angles here from A, then the deflection in A, B, the deflection in B, and then C, and the deflection in C. We have these opposite interior angles and this length, these lengths here. So deflection in B is equal to theta x1, which is this length there, and deflection in C is equal to theta x2, this length there. That angle is the same as that angle. So deflection in B plus deflection in C is equal to this angle, x1 plus x2, which equals theta length BC. BC right there. X1 plus X2 is just length BC with this angle here multiplied out front. So plugging it in, we have deformation here plus the deformation here. This is deformation in B, deformation in C is equal to theta times 0.225. Where did we get 0.225 from? I think that would be LBC 225, right there, length BC. So we can find that angle is equal to 7.887 times 10 to the negative 8th P. And then similarly, deflection in A minus the deflection in B is equal to this angle length AB, or AB. Groovy. Okay. Now plugging this in here with P and that in with P. Let's see, with this angle here. And this would be just, let's see, deformation in A maximum, and then this would be deformation in B again. This in terms of P, this in terms of P, multiply this through, solve for P, and then P is equal to 14.74 kilonewtons. And we know that tan theta for the angle here, deflection in B over x1, deflection in B equals x1 tan theta for small angle approximation, tan theta is equal to theta, so that we know that deformation in B is equal to x1 theta. And that's how we kind of get around the more weird trig stuff. It's all hocus pocus. You just kind of have to know it intuitively. Don't try to understand this stuff. You'll lose. It's a losing battle. That's what I get from chapter 2, that is. Uniform versus non-uniform cross sections. Okay. For uniform cross sections, you can use pli. And theta is P over A. And elongations, or what's this? Engineering strain is equal to deformation over L. For non-uniform cross-sectional areas, you need to take the integral from 0 to L of P EA dx, or the sum of all the P, L, E's, and A's. So that's also worth writing down. Okay. This one looks non-uniform. The cross-section at least, right? So we're going to have the deflection in AB, the deflection in BC, or deformation, I mean, and the deformation in CD. Deformation in CD is going to be equal to the deformation in AB. So we'd only need to find deformation AB. And we'd also need to find deformation BC. And we'd just double deformation AB for BC. Well, it would be the same, so it would be equivalent, but we would say AB twice because that's the same as CD. And they're opposite, so. Okay. So deformation AB. PAB, which is 350. LAB, 1.6. E of AB, we're given that this whole thing is a sheet of vinyl, which is 0.45 times 10 to the 6 psi. And this is 1 inch by, let's see, it's a 1/4 inch thick. So it's 1/4 cross section. So boom, deformation AB done. Deformation CD is equal to AB, so we also have that. Now for BC, the deformation in BC is going to be, let's see, PBC is going to be similarly 350. LBC, 2. EBC, same thing. ABC, this time is 0.4 times the thickness of 1/4 inch. And then, boom, we have it right here. So now we just sum up all of our PLEs and A's. So sum up the deformations. Deformation AB plus deformation BC plus deformation CD. And all of that should equal 2.55 times 10 to the third inch. Just like the teacher did, I am going to skip right over this horrible, evil problem. Everything in chapter 2 is evil. You will learn that to be true. Now, problems involving temperature. Okay? Change in length. So, the temperature problems. Strain temperature is equal to the coefficient of linear thermal expansion times the change in time, or change in temperature, change in temperature times the length. Change in temperature is temperature final minus temperature initial. That should be fine. And I will note that this thing is going to be equal to 1 over F, 1 over C, 1 over K. Don't worry about what this is almost spelling, right? Internally, subliminally, that is what everyone is thinking when they're going through chapter 2 anyway. Things have a way Freud has proven that they just kind of come out that way. Don't worry about it. It won't hurt nobody. Those thoughts are fine. Normal to have, in fact. So, P is equal to, goodness me. Okay, so now we have the whole temperature block here. Let's see. Knowing that a 0.02 inch gap exists when the temperature is 75 degrees F, determine the temperature at which the normal stress in the aluminum bar will equal negative 11 ksi, the corresponding exact length in the aluminum bar. Oh, and what is the corresponding exact length in the aluminum bar? So we have the A of aluminum, E of aluminum, and the thermal, what was it even called? The coefficient of linear thermal expansion right there. So we're asked to find, so we have given the stress here. So we have negative 11 E. They want to know the temperature. So they want to know the change in temperature. And we know the initial temperature. So that's where we would plug everything into this equation here, I believe. And change in length due to P. Oh my goodness. Change temperature T. Oh, because we have two different ones. So you have to do the whole process twice. Change in temperature right there. Temperature final minus temperature initial 75. Here we go. Then boom, temperature final 202. Change in length of aluminum. It's a little bit racy, but you can kind of see the process here, and so much of it is gone. It's funny to me though. And here we have an example of, I would say this is a non-uniform cross section. And here we're rearranging the things because we know that the deformation in the aluminum is equal to the deformation in the what is it, brass. So when this plate goes down, it's going to deform all of them equally. So it's equal deformation, which means we can set this plea equal to the other plea. And what are we solving for? We're looking to find it looks like they're trying to find P. We're not given P. That's why. So we're looking to find P. So instead they're setting them equal to each other in terms of P. And as you'll notice that there's, let's see, is it twice as much brass as there is aluminum? There would be probably the same. But they're saying that it's a aluminum is equal to PB over 2. So it's 1/2 brass. 1P aluminum is 1/2 brass. That could work out like that. I could see that. They're setting it all equal here. And here's the 2 from our equation right there. And then we plug in the values. And see, lengths go away. EA. There's E, 70. A. 2 times 60 times H. Okay, so then we're solving for H. And that's going to equal 105, which is here. 2400, which is probably the area that they found with this. Times this, over 2, there's the 2, and then they solve for H. And load P, we're going to plug P in right here. PA plus PB is PB over 2 plus PB, which is 3/2 PB. So P is 3/2 stress times area, which is 3/2 80 times 2400. So P is 288 kilonewtons. Skip example 10. Poisson's ratio. Goodness. This chapter never ends. Poisson's ratio. V is equal to the negative of the absolute value of the lateral strain over the axial strain. Or, I guess, the engineering strain in Y over engineering strain in X, or the engineering strain in Z over engineering strain in X. So and pretty much what this means is that when you deform something, squishing it this way, it will also, or yeah, when you compress something this way, it'll push out the sides, and when you stretch something this way, it'll shrink in the sides. You'll see it here, right? As this is being stretched, its original shape here, it's getting thinner and less tall as it's getting longer. That's Poisson's ratio. Hooke's law is kind of like the big version of this. So Hooke's law. We're going to have EX, EY, and EZ. Very tedious to write this stuff out. There, boom. So this is generalized Hooke's law. All right. Here's an example using Hooke's law. EX is equal to deformation x over L. Deformation in x is EX times L. I guess that's from this here. The E is equal to deformation over L, yeah. So using this, stress in x over E times L, that's going to equal deformation in x. That's A. Y here is deformation in y is equal to EW. It's just like that's EX is loud. So then the Z would be EZ thickness. It's probably worth noting. You could probably generalize Hooke's law like this. So I'll note that very quickly. Let's see. Deformation x equals EX length. Deformation y is equal to EY width. Deformation in z is equal to EZ thickness. Change in area. Oh my gosh. We have no more space and we still have so much chapter. Oh my gosh. Well, it looks like a lot of this chapter is probably blank. Composite materials. Saint Venant's principle. This is for right here. Stress concentration factor. Stress max over stress average is K. And this is for anything using fillets. So like here, right there. We're going to need that, PK over A. And then there's the summary. So I guess I will try to write down St. Venant's principle. Concentrated loads result in larger stresses in the vicinity of the load application point. All right, here's some pictures right there of the strain. Discontinuities cross-section may result in higher localized concentration stretches. This is the stress concentration factor K. We'll just quickly, right here, right in that K equals stress max over stress average. Say that. RD. K is 2.05. Where did we find that? Not given, is it? I think that's us. That's them giving us where it is. R over D, D over D, 2, 1.6, 2.05. Stress max P over A. Stress max PK over A. Okay. And there. We also have these stress strain curves going up on the stress, hitting the point, and then going over and finding the corresponding value of K. That's probably where we found this stuff. For fillets, we found the K here, but 8 kilonewtons. That's kind of how we do it. I'll have to brush up. Here's the explanation right here, but this chapter we completely run out of room here. I think we covered mostly all of it. Tau, G. Do you have anything that has a G? What am I missing? What's much missing? G. G. Is this slide missing things? Oh, shearing strain, modulus of elasticity, right here. This stuff is importante. Oh, geez. Shear strain, shear stress. Elastic limit. And I feel like this should have stuff on it, but no. Oh, right in this corner here. Okay. So yeah, that's this answer sheet. Can we get a problem done real quick now? Here's our problem, deformation. Now remember that deformation is equal to PLEA. Looks like we have E equals 70 gigapascals. P is equal to 115 kilonewtons. L, we can find easily. Let's see, deformation at point B. Here's point B, so that's 1.75 meters. PLE, we need area. Area equals 800 millimeters squared. So deformation is going to equal 70 times 1.75 times E, which is, whoops, sorry, this should be P, 115 times 70 times 800 millimeters squared. So this is not going to be the right, because we don't have times 10 to the negatives, but this should be the right numbers. 115 times 1.75 over 70 times 800. Not quite. Ratios, that's how ratios work. This is going to have to be e to the 6th, and this is going to have to be e to the 3rd. How about this? It's not going to be 115 then, will it? Because it's going to be 75. So it's going to be 115 minus 50 minus 75 is going to be equal to RA. I'm going to be solving for RA. So 115 minus 50 minus 75 is negative 10. So I'm just going to say that RA equals 10. I'm going to put 10 in here instead. Okay, yep, and I'm getting 0.3125. So the deformation was caused by the reaction at A on point P, not just force P. So that's millimeters. That's how you do a chapter 2 problem. That's the chapter 2. Break is here. So let's go on break. And then we'll return for chapter 3.
With his right, Larry finished with 47 points, 14 rebounds, and 11
Oh no,
assists,
the mic is on.
including a game-tying shot.
Okay, we're back. So let's get to studying the final chapterino. So this is going to be torsion, chapter 3, torsion. So the outline, let's see. Torsional loads on circular shafts, net torque due to internal forces, shearing strain, stresses in elastic range, normal stresses, torsional failure modes, range. See, sorry, I was reading that backwards. Angle of twist in elastic range, statistically indeterminate shafts, design of transmission shafts, stress concentrations, torsional loading, loading by couples. Okay, right here. Counterclockwise, counterclockwise, F, negative F, that's a couple right there. Examples of torsion here. Torque, T, is a couple. Axial loading, P, elongation, sigma, I think that is. Normal stress, I don't know the names of these. Maybe that's omega, I don't know. So I'm just going to say deformation, and this is just stress. Normal strain, torque is T, twist angle, shearing stress tau. This one I think is actually omega. I take it back. And then G, I forget what the G is. I had the other sheet, but I had to get rid of it for this one. Torsion, torque. Stress and strain in members of a circular cross section are subjected to twisting couples or torques. Shaft transmission, the torque to the generator creates on equal and opposite torque. So generator, I believe that's probably just something that can be just a shaft or something that can hold the rod here, and that's going to be twisting here. Or maybe that's the generator. Yeah. Torsion. Transmission shaft of a car, kind of like what we saw here. Torsion rod, torsion tube, torsion bar. Torsion is R cross F, just like how a moment is R cross F, which is a distance times a force. Interesting. So there's the transmission, there's the drive shaft, final drive, engine, torque converter. So this is basically the layout of how a car works. Net torque due to internal stresses. Internal stress tau is produced due to the torque T. And let's see, dt is, what is this going to be, the force here? Derivative of the force times the lever arm. Okay. And then we get this internal torque. Tau is Fa, and this is how we get this, I guess, derivation right here of the dF is tau dA. So this is definitely something to write down here now. I spell T-O-R-Q-U-E. It's going to be T equals okay. And that's the internal torque, and I will also note that that's a lever arm. Do I need to know this? Proportional. I don't think we need to necessarily write that one down. And then here we see axial shear components. As you can see, everything is straight here. And when we apply the couple, the torque, that it's deformed a little bit. All the lines that were straight are now on a bit of an angle here. They don't entirely go along the length of this. They rise a little bit. So it's been deformed slightly. Shaft deformations. From observation, the angle of twist of the shaft is proportional to the applied torque and the shaft length. So this is the proportionality of the twist angle and the torque. When subjected to torsion, every cross section of a circular shaft remains plane and undistorted. That's interesting. So I guess that's just cross section then. But clearly on the outside you can see deformation. But I guess if you cut the center of it and you just look at the shape of that, then it won't be deformed. I would have to say that to an extent that's true, but that has to be untrue at some point. Ah, well, it says it isn't. I would assume that at some point they would break, and when they break, maybe the cross section looks different. But I'm wrong, I guess. Cross section's the same. Shaft deformations we see here again. Perfectly straight parallel lines. Now they have a little bit of a twist on them, and you can see the angle here. They actually show how far it's twisted. Shearing strain. Here we go. Here's something to write down. Whoa, wrong thing. That's probably good. And I'll also write C is radius of shaft. Shearing strain produces an angle of twist. Looks like we have a few different ones here. Oh, we're running into Chapter 3, Equation City. Equation City. Oh, jeez. So this is quite a bit of quite a few equations now, isn't it? So looking at these stresses in the elastic range, multiply both sides by G. So we just got a lot to write down here. So let's just write these down now. So this is shearing. I think it's also shearing. There was a key up here, wasn't there? Shearing stress, shearing strain. Oh yes. Let me get out my trusty I almost said calculator. But no, this is not a calculator. This is in fact, ruler. Right about there. Okay, we have entered Equation City. We already have that one. I can't tell if that's T max. Like tau max. It looks like it should be tau max. But most of these are straight lined. And they should be curvy lined. That's interesting. But this one's got a bit of a curve. Same with this tau has a curve. See that? J is the polar moment of inertia. Looks like this supposed to be over C. Okay. So that's good. Just a bunch there. And normal stress. Elements with faces parallel and perpendicular to the shaft axes are subjected to shear stresses only. Normal stresses, shearing stresses, or a combination of both may be found for other orientations. So I guess this is only at angles. So it can't be parallel or perpendicular to the shaft of the axis. Very interesting. If element is at a 45-degree angle to the shaft axis, then stress is equal to tau max. That is interesting to note. That's something I probably will actually note down. Okay. Element A. Is that A? Pure shear. This one's shear plus normal, I think. I can't tell if that's A and B. Maybe that's A and B. Torsional failure modes. Ductile materials generally fail in shear. Brittle materials are weaker in tension than shear. Interesting. When subjected to torsion, a ductile specimen breaks along the plane of maximum shear, i.e. plane perpendicular to the shaft axis. When subjected to torsion, a brittle specimen breaks along the plane perpendicular to the direction which tension is maximum, i.e. along the surface at a 45-degree angle to the shaft axis. Right there. And here we have our first example. For the stress, for the cylindrical shaft shown, determine the maximum shearing stress caused by a torque for magnitude T equals 800 Newton meters. So we have a radius, so this is our C. We have T equals 800, so we have C and T. And that's what's tau max. J is pi over 2 C to the fourth. So let's see. Tau max, TCJ. We have everything. Plug it all in, boom, right there. Example 2, knowing that an 8mm diameter hole has been drilled through each of the shafts AB, BC, and CD, determine A, the shaft in which maximum shearing stress occurs, and B, the magnitude of that stress. So we're given what TAB is. I think these tell us. It's a little too small for me to see from here, though. So we know that TAB is 48 Newton meters. And we also know C1 and C2. So we can know J of AB. From this we can get tau max, which is TAB, CAB, JAB, plug and chug. And then we can do the same for the other shaft, which is BC and CD right here. This is the magnitude of the stress. Maximum shearing stress occurs. Looks like we found tau max, which is, is it strain or stress? Tau. Shearing stress. Oh, and the magnitude of that stress. Okay, so that's just the positive and negative. It's just the positive of it. So yeah, there it is. Oh, wait. Yeah, I think that's that. 3 assumptions. Torques applied at the free end. Every cross-section remains plane and undisturbed. Each cross-section rotates as a rigid slab. All equally spaced circles rotate by the same amount relative to each other. So angle of twist in elastic range. So it looks like we have that one. BCG. We do not have this one. That'll fit right there, won't it, though? Oh, but we have more angles, so... There you go, close enough to a G. And probably should have one for this here. But I'll just write that down here, angle of twist. Okay. Now we have statistically indeterminate shafts. Given the shaft dimensions and the applied torque, we would like to find the torque reactions at A and B. From a free body analysis of the shaft, TA plus TB is equal to 90 pound-feet. Right there. Too many reactions and not enough equations, statistically indeterminate. Compatibility equation. This is something we'll have to know. Would this here be the compatibility equation? TAL G1 J1 plus that equals 0. Let's see, we have three more examples. And then, so many more equations. So many more equations. Where are we? Right here. I feel like this could be the compatibility equation. Let's see how it's used here. So, under normal operating conditions, a motor exerts a torque of magnitude TF at F. The shafts are made of steel, for which the allowable shearing stress is 12 ksi and have diameters D, CDE is 0.9 inch, D, FGH is 0.8 inch, knowing that RD is 6.5 inch and RG is 4.5 inch, determine the largest allowable value of TF. So FG1, FGH is equal to 1. Must be given in the diagram. T1 is, let's see, tau allowable, J1C. I don't see that in the equations, actually. Maybe that's, I see T max. That's different from T allowable, though, right? TCJ. Tau max equals TCJ. I guess T allowable also works. That's something. I could probably write that. We probably have enough space. They plug in the values for J. J is solid circular pi 2 C1 to the fourth. Yeah, these look like they could be pretty good equations to write down. That T allowable is equal to, or T is equal to T allowable pi 2 C to the cubed. I think I'm going to write that one down. Because this could save a lot of time. And then we plug in the values, and then we get T1. We know CDE. We actually get T2 also. We have a gear ratio here, which, did we get that from this? I think I should probably write down the compatibility equation anyway. But instead I'll write this up here. Looks like I have some space, I'll just put it right here. Is this the compatibility equation here? Where'd they get this from? Where are they getting everything from? They just make so much stuff up, it's hard to keep track, man. Oh, wait. Right here. Boom. Got it. So we're given the angle of twist, which is in radians, and you have to get it into you have to get it into degrees. So they have degrees, converting it back to radians to make it the equivalent to this here. And it looks like they're solving for t. And we find t, and that's part A. B, determine the angle of twist. Is applied to a solid cylinder instead. So now they're setting L2 equal to L1. Here we have one, we have to integrate this one, right? Yep, there's an integration. What's this here? This is one to have right here on a note sheet. This one worked out. I'll see if I have that one in my note sheet. But they're using small angle approximation where the angle here is equal to C over L, which we could probably use all this too. But it would be good to have the diagram to look at also. And then they integrate, plug in the values, and I don't know what this means. but I don't think we really went over this too deeply in class. But here, now we have a design of transmission shaft. More things, more things, more things. Okay, we have V is equal to R omega. Omega is equal to 2 pi frequency. T is equal to T omega. T is equal to T 2 pi frequency, or T is equal to T over omega. Tau max is TC over J. Yep, we have that. We're going to have solid and hollow. I'll just write it here. So they're solid and hollow. We also have P is equal to FV. P is equal to FR omega, which is equal to P is equal to tau omega, which we have here. Okay. And I'll also probably write that W is equal to RPM, and that P is equal to watts. Using allowable shearing stress 4.5 KSI, design a solid steel shaft transmission, 12 HP at a speed of A, 1200 RPM, and B, 2400 RPM. So the allowable shearing stress, TL, is 4.5 or 4500 KSI. Omega is 1200 RPM. So what are we asked to find? A shaft. So there'd be, I guess they're asking for the diameter. So let's see. Right here. So T over tau max is going to be equal to pi 2 c to the cube. So we're going to be trying to find c. We know tau max. And what is t? We have p. T, or t is p over w. We can write this as p over w tau max right here is equal to this. And now we plug in the values and we solve for c, and the diameter is twice that. So we have the diameter here and here. Stress concentrations, tau max Tc over J, we have that here. Stress concentration factor, K. Okay. Okay. Just gonna make sure it says smaller radius right there. Example 7. The stepped shaft shown below, 40 kilowatt at a speed of 720 RPM. Determine the minimum radius R of the fillet if an allowable stress is 36 MPa of 36 MPa is not to be exceeded. So we given P, we know W, and T allowable. So we know what the tension is, or torsion, sorry, torque. You know what? Gosh dang, we know what torque is because we have P and W. So here we have it here, and with our equation that we just wrote here, K T C J. Let's see. We have C. We have the C's right here. So K, what's K equal to? We might need to have a diagram here. K of 1.24. Or no, we solve for K here. Okay, now that we know K, we can plug K into this, I'm sure. Is this what K is for? Yep, K, 1.24. 1.24 is probably, there's 3, so there's half. 1.24 is probably here. So we're looking at d over d of 0.24. These are difficult to read. So right there, that's what we're looking at. So R here is going to be 10.8 millimeter. Okay. Example 8. We have to use a compatibility equation for this. So I probably should write down the compatibility equations, and that's all we should know. That's all we should need to know for this. Where were they? Right here, compatibility equation. Oh my gosh. So here we're going to have that angle of twist 1 plus angle of twist 2 equals 0, which means that TA, LA, should that be a 1? TB, L1, J1, G1 equals T, B, L2, J2, G2 equals 0. Why did I say equals? That should be plus. Plus. So these are the compatibility equations. And we have, let's see, the solid cylinders are AB and BC bounded together at B and are attached to fixed supports at A and C, knowing that the modulus of rigidity is 3.7 times 10 to the 6 psi for aluminum. And so this is going to be G for both of these. G is modulus of elasticity. So we have G for both. Probably going to be using this here. And the rest is given here. We have TAB, LA, JA, GA. We have this, and then we have the. So now we have we can get the angle AB in terms of TAB, and the same thing here. We can get the. What do we solve here? The angle BC in terms of BC, and with the compatibility equation, we know that angle AB is equal to angle BC. We can set them equal to each other. And now we can get TBC in terms of this ratio, TAB. And how do we manipulate it into that? Would that be the... I don't have my calculator on me right now, but 6 twice is 12. And that's a 0.5, so it's probably going to be these multiplied together. TAB plus TAC is these multiplied together. Interesting. I don't know the exact manipulation there. But from this, they can get TAB and TBC. Interesting. And with that, we know tau max, TAB, CAB, JAB. We can get tau max. And for BC here, we can get that too. Wait, 12.5. Is that right here? It is. Never mind. So they're going to plug this in here, TBC, and then this in here, or this right here. See, TBC would just plug right in. And then this for TAB, right? No, because this is equal to this. TAB plus this TAB equals this, and then you can solve for one, and then you can plug in for the other. Okay, now you can plug it in with your tau max, TAB, CAB, JAB, same for BC, BC, BC. Plug them all in and get your correct KSI values for your maximum shearing, I believe that's shearing stress. And that's the whole thing for torsion. Now let's solve the torsion problem. Is it a two-parter? Looks like it. So let's see what we're given. 2.15 kilonewton torque. So instead we could write that T equals 2.15 kilonewton. And we have a larger diameter and a smaller diameter, which is 50, which is 25, which means that the larger radius and the smaller radius equal 25 and 12.75? I believe so, yes. So now with this, we're asked to find the maximum shearing stress. Shearing stress is going to be the tau max, which we know from our equation here. Let's find tau max. Tau max is TC over J, and we know that J is equal to, for a solid, we have a hollow. So it's going to be pi over 2 C2 squared C1 squared. So that's going to be our J. Okay. So now, let's plug in our values. Is going to be TC over J is going to equal T times, I think we have to use the inner, so it's going to be 12.75 all over J, which is pi over 2 25 squared minus 12.75 squared. And oh dearie me, I think I do need to get my calculator for this. And it's actually not squared, it's to the fourth. To the fourth. Okay, quickly, I'm going to pause this and get my calculator. Oh no. Oh my gosh, I forgot we have calculators at home. So here we're going to have the second alpha, or second y equals, it's going to be, actually, what's t? Is that what we're solving for? We know t. It's 2.15. 2.15, 12.75, and this is going to be, whoa, pi over 2 times 25 to the fourth minus 12.75 to the fourth. Oh my goodness. Yeah, that looks probably about right. Not quite. So instead, oh wait, let's see. Ratios. This is in what, millimeter? Millimeters probably fine. We probably need to get that, however, into newtons. Newtons per millimeter is probably what we're looking for here. Looks like it's the same thing. And that's not quite right. So we have TC over J. Solid circular. We have hollow, which is pi over 2. C1/4 minus C2 minus C1. Mm-hmm. Is the up top C the right one? Is that one supposed to be... First off, what is 25 divided by 2 the right thing? It's 12.5. Ha! That'll surely throw an answer off, wouldn't it? So would this one then be 25 on top? Is it the bigger C? That's way too far off. The other one was close. It's close here. Newtons per millimeter. That's kind of what I'm looking for though, right? Is a megapascal? Yeah, I'm getting the same thing. It's supposed to be 87. I'm getting 93. Let me pause this for a quick second. Oh, I'm very stupid. They're saying consider it's a solid shaft. I was treating it as if it was hollow because I looked at the diagram. No, just they say consider it solid, so it's going to be TC over J, which is going to be 0.15 times C of 25 over a J of, well, what's the J going to be? J for a solid shaft, pi C to the 4th over 2. Or, yeah, that works. So now, there we are. That, and if we make 25, not quite, would have to be to the 6th. Yeah, 25e to 6, there you go. I think this should be to the -3rd and that should be to the 3rd, but if you just make that 6, it covers the difference. So there we are. I'm not going to do the second part of this, so I think this should be good. So there's at least one early problem for all 3 chapters and the entirety of the notes with creating a note sheet on the side. Hopefully that's good exam review, at least a little bit. It will never replace actually doing the problems, so I highly recommend opening your book, going to Jeff Hansen's YouTube channel and just doing a ton of problems. That will get you much farther, but brushing up, knowing the concepts, reviewing on what exactly it is you're learning, and knowing what equations to use. That's a lot of it. That's a lot of it, but it's not all of it. So really go out there and do some problems. And yeah, hopefully this helps.